Okay, so continuing along in our discussion of phase changes, and I want to get into more of the descriptive component of phase changes. Okay, so no math on this lecture. We're just going to talk about some of these phases and what they mean. Actually, I lied. There's just a little tiny bit of math, and that's the Gibbs phase rule. Okay, so let's get into that right away. So Gibbs phase rule has an equation. It's the following: F equals C minus P plus 2. Okay, so what do all those letters mean? Okay, well, C is the number of components. Okay, so in other words, is it a pure phase? So if it's a pure, I shouldn't say pure phase, if it's a pure material, then that means C equals 1. There's just one thing, like water or helium or carbon dioxide. But we certainly can have multi-component phase diagrams. So that's very common, especially with lipids and proteins. You'll see that when you add things like water and salt to those types of materials, it can really change their structure. So for everything we're doing in this class, we're just going to stick with one component phase diagrams. In the next couple chapters, we'll see what happens when we have multi-component phase diagrams. Okay, so P is the number of phases for the letter P. Okay, and that's pretty descriptive, right? If it's a liquid, that's one phase. But for example, if you're at, let's say, the triple point, there's 3 phases at the triple point. Or for example, if you're on one of these phase boundaries, let's say you're somewhere like right there, that's technically 2 phases. You're in a situation where the vapor and the liquid are in equilibrium with each other. Okay. And so last, F is the number of degrees of freedom. And this isn't quite the same degrees of freedom like what we talked about with rotations and vibrations and so forth. This degrees of freedom is really like how many things can I change and still maintain the same phase. Okay, so for example, if I'm somewhere like right in here, let's say I'm at this point, then I have 2 degrees of freedom. I have changes in temperature. So I could change the temperature, so that counts as 1 degree of freedom, or I could change the pressure. Okay, so that counts as a degree of freedom. But if I'm at, one of these points right here, then that changes my degrees of freedom. For example, at the triple point, you have 0 degrees of freedom. You can't change the temperature or pressure at the triple point and still maintain the triple point. Okay, so let's work through a fictitious example. Okay, so this is an activity. So I identify the number of phases and degrees of freedom at each point indicated on the graph. Okay, so we've got A, B, C, and D. So here's point A right here on this line. Here's point B at the intersection of phase A, alpha, phase beta, and phase delta. Here is point C, which is actually now the intersection of phase delta, beta, gamma, and phase eta. And point D, right, is like right there in the middle of phase alpha. Okay. So first, let's identify the number of phases for each of these. So P, because the equation, right, recall, is F equals C minus P plus 2. So we know for everything here, C equals 1. So this is a 1-component phase diagram. Okay. So what about at point A? Well, at point A, we have, it's on one of these phase boundaries. So there are 2 phases in equilibrium with each other. Okay, phase alpha and phase beta are in equilibrium with each other at that point A. What about point B? Well, it would be 3. right? You can see there's phase delta, phase alpha, and phase beta. Okay, what about point C? Well, that's 4 phases right there, right? So that's right phase delta, beta, eta, and gamma. And then at point D, there's just 1 phase indicated by that set of conditions. So now what about the degrees of freedom? Okay, well here A, so we'll say F equals 1 minus 2 plus 2, so that equals 1. Okay, and we're going to talk about what all that means in a second. Okay, so for point B, F equals, okay, the number of components is C, right? And that's, let's see, minus 3 plus 2, and that equals 0. Okay, for, we'll say A. For B. Okay, what about for C? Well, F equals 1 minus 4 plus 2, and that actually gives me -1, and we'll talk about what that means in a moment. Okay, and then finally, point D, I get F equals 1 minus 1 plus 2, and that equals 2. Okay, so what does all of this mean? Well, at point A, I only have 1 degree of freedom right there. And what that 1 degree of freedom means, I can't change the pressure without correspondingly having a change in temperature if I want to maintain having those 2 phases in equilibrium with each other, right? So in other words, if I'm changing the temperature and I want to stay on this point, I have to change the pressure as well, okay? So in other words, I have to change P of T, right? So I have to, if I'm changing T, then P is going to respond to that as a consequence, if I want to stay on that line. What about point B? Well, point B, 0 degrees of freedom, that's a triple point, okay? So I'm going to say TRP, triple point. I can't change the pressure or temperature at that point and still make it a triple point. So there's 0 degrees of freedom. I can't change temperature or pressure and still maintain that point. What about this point C? Well, you might be thinking, is that a quadruple point? And no, this thing is fictitious, cannot exist. D-N-E, does not exist. Okay, so I told you this was a fictitious phase diagram. And yes, as we will see, as we learn from Gibbs phase equilibria, Gibbs phase rule, you cannot have 4 phases in equilibrium. Can't do it. Okay, we can have 3 phases in equilibrium, but we cannot have 4 phases in equilibrium. It does not work. Okay, and now what about point D? Well, point D has 2 degrees of freedom, and that means at this point D, I could maintain the temperature and change the pressure up or down, you know, provided that I don't hit some boundary. Or I could maintain the pressure and change the temperature up or down as long as I don't hit one of those boundaries. Okay? So that's what all of this means with the Gibbs phase equilibria. And as it turns out, this holds even in really complicated phase diagrams. Okay? So I'm going to move past that, and I'm going to do more